broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. I hope you're ready to continue with Fly to Learn. I'm increasingly getting the feeling that we're basically going to ride through Fly to Learn to the end of the semester. So I think that it's probably a safe bet that this is what we're going to continue to do, which means that it's going to be a pretty relaxed pace. We're going to continue doing the flight testing during the class, and doing walking through the explanations and stuff like that. So it's going to be a bit of a relaxed pace, and then we'll probably be looking at like the end of the semester after that. Don't know 100% for sure, but based on how these things have gone previously, we may have like one or two lessons that are sort of their own thing, and then we would have the end of the class. But anyway, that's neither here nor there. Like I said, hope you're ready to continue. Unfortunately, apparently the videos did not record from Monday, so there are no videos from just this past Monday. But as I understand it, oh well, it's a good place to be. Cool. Was it like a competition or something? Oh, gotcha. Huh. Interesting. Well, that's pretty neat. But yeah, regardless, as I understand it, you guys were starting to do the testing for wing loading. So what I'm going to do is just really, really, really quickly do a review of what wing loading is and what you guys are supposed to do for your testing. And then we will get moving on the actual testing proper so that you guys can get that done. And then we will move on to the next lesson, which is going to be power loading, which sounds way more awesome than wing loading. Anyway, wing loading. What is it? Well, thank you, Malwarebytes. Wing loading is basically the ratio of plane weight versus wing surface area. I mean, put in its simplest form, it's how much does the plane weigh? This is my cartoon weight. Divided by, oh good lord, let me try that again. Divided by, there we go. Here's my aeroplane. Boom, 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 boom. Look at that gorgeous airplane. How much surface area your wings have. That is meant to be a grid overlaid on the wings. Let's pretend that it makes some kind of sense for now. So yeah, basically, the way you determine wing loading is you divide the plane's gross weight, so how much it weighs, by the length times the width of the wings, or wingspan times mean chord. And this gives you, well, it's a ratio. And the whole idea with this ratio is there is no one particular area on the wing that is meant to do all of the heavy lifting, right? Just like, if you pick up something with your, if you grab something and you pick it up, your fingers, presumably, distribute the weight evenly. It's not like even though you've wrapped your hand around a heavy weight, your ring finger is taking all of the weight and holding it up by itself. At least you'd hope not. It's kind of painful. But all of your fingers distribute the weight evenly. The same kind of idea with the wings here. The wings are lifting the plane into the air, but there's no one part of the wing that does all of the work. Presumably, the entire wing works to lift the plane. So the smaller the ratio is, that means that each individual sort of part of the wing has to lift less weight on its own, which means that the plane has an easier time taking off and, flying through the air and stuff like that. It may also mean that it has a harder time dealing with turbulence and stuff like that. But anyway, um, it is basically how powerful the wings are compared to how heavy the plane is. The wing loading ratio number can be decreased by either lowering the weight of the wing, or excuse me, the weight of the plane, or increasing the size of the wings. Likewise, it can be increased by increasing the weight of the plane or decreasing the size of the wings. As the number gets higher, each individual sort of square foot of the wing has to work harder and lift more. So just some really quick math. Let me get my calculator open. Calculator. Hey, hey. All right, so we got a calculator. The plane's gross weight is 2,500 pounds. The wingspan is 50 feet and the mean chord is 5. So what we've got here is 50 times 5 will give us the surface area of the wing. Yeah, see, like looking at a plane from the front. So the surface area of the wing is 250 square feet. That's because 5 times 50 gives you 250, the length times the width. So then we take the 250, or excuse me, the 2,500, which is the gross weight, and we divide it by the wing area, so 250. That gives us a nice round number of 10 pounds per square foot. So that means each square foot of wing has to lift 10 pounds, which is not so bad. I mean, that's pretty reasonable, right? Like, you guys can lift 10 pounds. I probably can lift 10 pounds. Um, you know, it's not so bad. But as we can see, if we do the math a little bit more, let's do the next one. So 40 times 5 is 200. So as you can see, the wing area is a little bit smaller. I say a little bit, it's smaller by a fifth, which is not insignificant. And then 2,500 divided by 200. Oh, look at that, 12.5. Hey, Ethan. Yeah, sorry, it's just a review for the people who are not here on Monday. So 12.5. It's just meant to be pretty quick anyway. So as you can see, now each square foot of wing has to lift 12.5 pounds. Not a huge increase, but still more than 10. And this happened because there was less wing. If you have 5 people all lift up a heavy bag, let's say that bag weighs 200 pounds. With all 5 people working on it, they each only have to lift, 40 pounds? Not too bad, right? Suddenly, one of the people decides that they don't want to lift the bag anymore, so you got 4 people lifting the bag. Now, each of those 4 people has to lift 50 pounds. Still, it makes a difference. Anyway, you get the idea here. As the wing size decreases, the wing loading increases. Just like if you had a heavy bag and you had fewer people lifting it up, each person would have to lift more weight in order to lift the bag. In essence, as wing area goes up, loading goes down pretty linearly. You're not going to have any crazy math like that or anything like that. It's pretty simple multiplication and division and stuff like that. Likewise, if we keep the area the same on the wing and we change the weights, we change the wing loading. So if we have 5 people lifting a bag and we change the weight of the bag, the lighter the bag becomes, the less the people have to lift. The heavier the bag becomes, the more the people have to lift. So similarly, gross weight and wing loading, as weight increases, wing loading increases as well. Again, Very linear relationship, very easy to predict. Then we had some questions, all meant to reinforce the same idea that if you increase the weight or decrease the wing size, you increase the wing loading, and the opposite is true if you decrease the weight or increase the wing size. Anyway, that's not why you guys are here. You guys are here to do the test flights. So I'll walk again real quick through how to do the test flights, and then I will leave you guys to do the test flights, and then we'll move on to the next lesson after you guys are done with that. So let me go ahead and get to the plane designer for X-plane. I wanted to call it X-wing. For X-plane, start it up. Plane maker. So here we got our plane maker starting up. As you can see, I still have a really super duper absurdly large wing plane in here. So here we've got our plane stats for each of these. So the idea is we change the wing size for each of these, and then the weights on the last one. And that's meant to illustrate the difference. So in order to do that, we go up here to standard and then wings. And for each of these, so for the first plane, which is named WL15, the semi-length is going to be 7.5 feet. And then under wing 2, you put in the lateral arm, 7.45, and the vertical arm, which is negative 0.85. And then we have our first very small wing design. And then you can just go ahead and save that as your first name and 15, since that one is a 15-foot wingspan. It almost looks like a plane from a kids racing game or something like that, like Donkey Kong Racing. Or was it Diddy Kong Racing? Anyway, whatever. That was 20 years ago at this point. Good Lord. So you want to do that for the 15. You'll also want to do that for the 30. So set it for 15. So the semi-length is 15 feet. And then the lateral arm and the vertical arm on wing 2 match. So 14.95 and negative 3.5. So then you've got your 30, and then you'd go ahead and save as, just like you did before. You want to save as because if you just save, what you'll do is you'll update your previous save file. So then you'll create a 15, save it under 15, then create a 30, and then save it under 15 again. Yeah, on the last plane, you will change the maximum weight. Limits. Nope. There we go. Oh, you are totally right. You increase the maximum weight on the other ones too. I thought these were the default values, but it turns out that I was thinking of I was thinking of the last time I did this. Well, that's silly of me. Yeah, you'll want to change the not the empty weight. The maximum weight you want to, yeah, you want to make 2,800. And then finally on the last one, the WL60, you want to change the maximum weight to 11,000 instead of 2,800. And then you'll want to change, so 380 pounds. So this is going to become 9,620. So you'll change the weight of the 60-foot plane to 9,620 pounds with a maximum weight of 11,000 pounds. And I realize it's a little strange, but it's just to sort of, it's to, I guess, to better illustrate the ratio, the wing loading ratio. So anyway, go ahead and get started on that, and I will keep this screen paused so that you can check the values, and then when you're done, you can, when you're done setting up the plane, you can then fly the plane. Also, when you're done doing the test flights, go ahead and raise your hand. All right, one person done already. Cool. Oh yes, taking forever to load. Good old X-plane. Hey, Ethan. Just a friendly reminder, if you're done doing the test flights, go ahead and raise your hand. Alrighty, give like everybody another 10 minutes for testing, and then we'll move on to the next thing. Sure. Okay. So let me pop it up. So for a given plane, you're going to want to change the wing information, and for the last one, you're going to want to change the weight and balance. So if you go into the wing screen, um, you just fill in the appropriate values. So in this case, wing one semi-length. Notice we're in the wing one tab. Just go ahead and fill the semi-length with whatever is necessary. In this case, let's put 30, so we have it uh, approximating the 60-foot plane. Then you've got wing two lat arm and wing two vert arm, in which case you're going to go into wing two and change those respective values. So lat arm is 14.9, or excuse me, 29 point, dope, 29.95, and vert arm is 0.55. And we make it positive. When that's done, you can close that out. Now we've got these wonderful long wings, and if you need to adjust the weights, you adjust the weight and balance here, in which case you set basically between the empty weight and the fuel load so that it equals 10,000. And then the max weights you set to 11,000. Otherwise, you set the max weight to 2,800 for the shorter planes. A plane with the longest wing wouldn't take off. Well then, I suppose that could be a little bit surprising though, or unsurprising though, considering. But yeah, once you've done all that, you can just go up here to File and then Save As, and then save it as your next awesome plane. It almost took off. It was getting there. Okie dokie. So I think we'll take a break from testing at this point. So I saw a couple people mention that the 60-foot plane doesn't really actually take off, and that's important to note because, well, what's the deal? I mean, the wingspan is twice the length of the of a 30 wingspan one. Yeah, it's that's the thing. Yeah, the chord is double the size as well, but the total weight is 4 times as much. So despite the fact that we're looking at an increased surface area, the increased weight outpaces it. So therefore, no plane taking off. Anyway, running a few tests and things like that, we find that there is a sort of a consistency here, where you might see that the average takeoff distance increases pretty dramatically. With a table, excuse me, that would represent these values up here. However, the constant, if there were a constant wing load, whoops, we'd be looking at a flat takeoff distance, as in there wouldn't be a change in the takeoff distance. So yeah, as the wing load is higher, the takeoff and landing distance is longer, the stall speed is higher. However, it has higher flight performance and it can carry a greater payload. On the other hand, a lower wing load means a shorter takeoff and landing distance and a lower stall speed, so it can fly slower before it starts running into a stall. However, the flight performance, it's not as maneuverable, and it can't carry as much. But enough of that, let's talk about power loading. So power loading is about horsepower, specific fuel consumption, and range. Well, actually, okay, so fine. Power loading is the ratio of weight to power. Engineers use power loading, which is a ratio, to predict airplane performance. I realize I just said it's a ratio twice, but whatever. They use it to predict airplane performance. Horsepower is a measure of power. An engine creates horsepower by changing the potential energy of fuel into the kinetic energy of turning pistons. So, in essence, if it's a piston-driven engine, let me just goodbye. If it's a piston-driven engine, what happens is you've got the piston, and it's actually attached to like a crooked kind of shaft, and you've got another piston down here, like so. Whoa, hold on. Let me redraw that piston head again. And both of these are in cylinders in which fuel is being injected. And as we know, fuel is explosive. And what happens to explosive things when they get hot enough is they explode. Why we call them explosive. However, there's more than one way to make a thing get hot. to make it explode, one of the things is we can increase the ambient temperature around it. So we can, using radiation, we can hold a flame to it, and the flame might make the air hot enough in order to ignite the fuel. That is certainly a possibility. It's also possible that we could, you know, heat up put it inside of a like an oven or something like that, and heat up the oven, and then between the radiation and the convection and you know, all that stuff, the air gets hot enough to ignite the fuel. Don't recommend doing that, by the way. Or you could simply increase the pressure of the air, because this is not pure fuel that's being injected in here. It's an air and fuel mixture. The air is the critical part of it, because if it was just fuel, the fuel itself wouldn't ignite. You need a little bit of like vapor and stuff like that. But yeah. But the air is actually another critical part of it, because then there's the oxygen and everything like that that's able to also help with the ignition process. But here's the deal. So this piston is moving upwards, right? And as it moves upwards, this is a poor drawing because this is actually a lot more airtight than my drawing would suggest. The air starts to get compressed, like squeezed more and more and more and more and more. And as it gets squeezed, because the pressure is increasing, it's actually increasing the heat of the air as well. Eventually, the air gets so compressed and so hot that the fuel in the fuel and air mixture explodes. And then that explosion forces the piston back downwards. Because these two are connected, that forces this piston upwards. And this is actually further connected. Let's say it's connected to the propellers. And what it's doing is it's making this shaft spin, and it's spinning up this way, which is forcing this piston upwards, which is repeating the process over here. The air in here gets compressed until it's hot enough to ignite the fuel in the air-fuel mixture, forces this piston down. Oops. Forces that piston down and forces this piston up. And the whole thing with this is the shaft down here is continually spinning in the same direction. It's the pistons moving up and down forces the shaft to continue to spin, which is causing the propeller to spin, which is causing the plane to move forwards. So that's how the potential energy of fuel is turned into kinetic energy of making the pistons run. Yeah, these pistons turn a shaft that turns the propeller, which acts like a wing to pull the plane forward. The power of the engine is called brake horsepower. The prop converts about 80% of this power pulling the airplane forward. This is referred to as thrust horsepower. Finally, engines wear out quickly and gas mileage is diminished when they run at full power. Therefore, airplanes are usually flown at about 75% of thrust horsepower. We refer to this power setting as cruise horsepower. So you've got brake horsepower, thrust horsepower, and cruise horsepower. Brake horsepower is the raw power that the engine creates. Thrust horsepower is the amount of forward power that the plane experiences after you know, the bleed off from brake horsepower being converted into like heat and other stuff like that. And then cruise horsepower is basically the maximum safe amount of thrust horsepower that a plane can experience for an extended period of time. Makes sense. So you may be thinking right now, wow, it takes 3 calculations to find out just how much power is needed to fly. Yeah, so yeah. Engineering is math. You don't have to be amazing at it, but just a solid foundation in math. I'm not amazing at math, but I can still do stuff, probably. But I believe in you guys. You guys can do it. You can earn a lot of money doing things like designing airplanes. Yeah, it does take a lot of math to get a rocket into space. This is true. So we will increase the horsepower of the plane to examine its impact on weight-to-power ratio or power loading. Listed below are engines with different horsepower ratings. Please calculate the power-to-weight ratio. Please pay attention to the trend. Feel free to do this on a spreadsheet or use a calculator. I'm assuming that the power loading, oh, they don't even care. All right, so horsepower. So if you've got 150 horsepower divided by 2,500, that means our power loading is 0.06. Likewise, if we've got 200 horsepower and our weight is 2,500, we've got 0.08. Yeah, that's me. English.exe has stopped working. If you've got 300 horsepower divided by 2,500, it's 0.12. There's a point there. And finally, 350 divided by 2,500 is 0.14. That's 5. I know how numbers work. So as you can see, our numbers, go up pretty gradually, pretty linearly. If we were to graph it, it would look something like that. Just a straight line, straight diagonal line. Pretty straightforward. Which means that it can be pretty easy to predict how much exactly the ratio is changed by changing the weight or the power. So calculated the power to weight ratio when the power stays constant and the gross weight decreases. So wing loading and constant horsepower versus decreasing gross weights. If the horsepower stays constant and the gross weight decreases, geez, what happens to power loading? Any guesses? Well, hold up. So horsepower stays the same, but gross weight decreases. Does power loading go up or down? Yeah, goes up. Because it's horsepower divided by weight, right? So as the weight decreases, our power loading increases. So the plane has a higher power loading. And it would look probably something like that. Again, straight diagonal line, pretty straightforward, pretty easy to predict. So our 275 horsepower airplane has a gross takeoff weight of 2,500. What is its power to weight ratio? Well, 275 divided by 2,500, look at that, it's 0.11. Cool, that was easy. Our small private plane carries 4 passengers. The plane weighs 2,400 pounds. The airplane's required brake horsepower is rated at 150 horsepower. What is the required thrust horsepower? How powerful must our engine be to fly at 75% thrust horsepower or cruise horsepower? So remember that about 20% of our brake horsepower is lost in translation to thrust horsepower. So if we multiply 150 times 0.8, we get our thrust horsepower, which is 120. Now, cruise horsepower is 75% of thrust horsepower. It means we're just multiplying this by 0.75 again, which gives us 90. Our cruise horsepower is 90. That's pretty straightforward, right? So I have a power to weight ratio of 0.09 horsepower per pound. The plane weighs 2,600 pounds. What is the horsepower of the aircraft? So if we've got horsepower per pound and we want to turn it into just horsepower, we need to multiply this by pounds, because what it'll do is it'll cancel these two out and we'll be left with horsepower. So sure enough, if we, one second, there we go. If we are to multiply 0.09 times 2,600, we're given 234. That would be the horsepower of the aircraft, 234 horsepower. Alrighty, so let's go ahead and, oh my, 7:51. Now that we've gone through all that stuff, let's go ahead and do the poll questions. And then you guys can pick up on Monday with actually starting on the testing. So that's a good place to stop. Realize it's not quite as exciting because it was a lot of time spent me talking at you guys, but hopefully it made sense and you guys will know kind of what you're getting into when we start on that on Wednesday. Yeah, I'm gonna go ahead and do the poll questions, and then if you guys have any questions about anything, here. Otherwise, you're more than welcome to head out. So here we go. First poll questions incoming.